So what first thing I'll do is introduce Frasier Burton. Frasier is our host for this 5 days. He's also the Senior Manager of Network Physics and DT's Applied Research Department. And once again, for those of you that were on the call yesterday, we learned some interesting facts about Frasier, about his ability to build an electron magnet that short-circuited his parents' house. I'm still not real sure about the electrifying wet brass, but there's been a few other experiments as well, like putting sodium in a bathtub of water, which, I mean, that was just, I'd love to have been there just to see that at the end of the day. So he is a true researcher and experimenter in this kind of space. And so, Frasier, on that note, I'll just hand it over to you. Thank you.
Thanks, Mike. I think my health and safety record has now been significantly damaged by those comments, but sadly they were all true. But anyway, welcome again if you were with us yesterday, or welcome afresh if this is the first time you've joined us. So as Mike said, this is the second day of the 2020 Tommy Flowers Network conference, which we're calling Let's Get Physical. This is a celebration and a showcase for the fundamental role that physics and physicists in particular have in shaping our digital future. We have lined up some top-level presenters throughout the week. This is our second day, and our speakers are from across industry and academia. And each day we have experts specific to the topic we're dealing with in that day. We have already had and will continue to have some very lively discussions, and there will be plenty of opportunities for you to ask questions. This is the 4th year we have been running these conferences, and I'm delighted to say that we have more attendees this time than ever before. That really is very much a consequence of being online and the pandemic. It's been, I think, truly a very challenging year for everyone with the lockdown and the impact of COVID-19. And if it's underlined anything, it's really reinforced the central importance that communications and telecommunications has now in our lives. Virtually our entire industry is working from home now, and to be honest, just 10 years ago that would have been almost impossible. But now it's working quite well, which is nothing short of remarkable. So the purpose of the Tommy Flowers Network is to bring together the communications and IT industry, together with both UK and international academia, to really focus on developing the skills and the knowledge of our future research leaders who are our present postgraduate researchers. It's worth explaining who Tommy Flowers was, in case you don't know. Tommy Flowers was a wartime communications engineer. He worked for the GPO, which was a predecessor organization to BT. He worked alongside Alan Turing in the code-breaking effort, and he developed the world's first electronic programmable computer called Colossus. Tommy is one of our heroes because he is an excellent example of how industry and academia can come together to make a really significant impact to society. So he brought his operational experience of working with exchanges and working with valves, and he combined it with the algorithm design from the University of Cambridge and with Alan Turing's insights to build the Colossus solution. So this is our second day of the conference, and we're focusing on wireless communications. Now, the physicists among you will notice that radio frequencies and the optical spectrum are basically the same thing. It's still just electromagnetic waves. There is a small matter of a factor of 100,000 difference in the wavelength, though, so that will make a significant difference in the way in which the radiation interacts with matter. So today we're focusing in on the lives and the achievements of physicists and engineers who are using the physical properties of the electromagnetic spectrum to extend the capabilities of wireless communications. So we have three speakers today from industry and academia. We have Maria Cuevas, who is from BT Applied Research and heads up the Mobile Core Networks research team. We have Frank Mullany from Nokia Bell Labs, and we have Professor Robert Piechocki from the University of Bristol. So I am now delighted to hand over to our first speaker, Maria Cuevas.
Thank you very much, Fraser. Can you hear me okay first? Just checking.
I certainly can.
Okay.
Good, Maria.
Let me just start by, I suppose, a bit of an overview of where mobile industry is heading. Most of you would have seen this or different incarnations of some of these diagrams here. But I suppose one of the biggest or the first initiatives trying to imagine what a 5G-enabled world would look like was this alliance called the NGMN, the Next Generation Mobile Networks Alliance. And they came together, operators came together and wrote a white paper back in 2015, which is where that triangle that you can see in the picture comes from, which is pretty much saying that we want to be more than just, if you like, internet access providers from a mobile perspective. We want to be enabling a myriad of future services for different industry verticals. And as you can see there, I won't go into too much detail. You can read the paper. There is a link on the slide. But in essence, anything to do with machine-type communications, supporting millions of machines per square kilometer potentially in the future. Also, what they call mission-critical communications, which would require potentially below 10 millisecond latencies to be delivered for certain use cases, and ultra-high reliability in order to support both those, and of course continue to support the speed and capacity required for mobile broadband communications, especially driven by video. So that was the ambition that was set by the NGMN white paper. Effort across industry to expand it space to use cases and revenue sources that I was referring to earlier. So I think internet access on being having the flexibility to address the pictures in the diagram, but it ranges from the healthcare scenarios like remote diagnostics, for instance, all the way to things like remote control of autonomous drones, smart cities, smart logistics, supporting energy industries, and emergency services teams. As I said, industry has made a lot of efforts within the standards body. The third has made an awful lot of effort in finding technical specifications for that. We need a rich ecosystem that comes together the devices and the applications and the open architectures and innovation can actually make all this true. So we're thinking that now we have a time where research and innovation is as important to take our industry to where we want it to be in 5 to 10 years' time potentially. If I move on to the challenges I suppose that we face are any chart that you look at, whether it's historical data or potentially forecast data, which is that the data volumes over the mobile networks are only year by year. The chart on the left side that comes from the mobile consumption in the UK has increased 4 times on average. Likewise, on the right-hand side, this is a forecast by Ericsson on the global of mobile traffic, and this is saying that effectively the increase is actually going to be even faster in the coming years with the emergence of 5G and new use cases. If I move on to the next slide, oops, I'm not. Sorry, I'm not. Oh yeah, sorry. Just to reinforce the point that we need industry and the mobile industry in particular to achieve both significant cost reductions as well as the ability to support new services for increased revenue sources. Let me just step back and try to see if I can, I suppose, set the scene to see if, sorry, I'm going to turn off the video because I'm being told that the audio is a little bit choppy, so I'll stop the video now just to allow for more of my voice to come through. Hopefully that works better. I was trying to explain that mobile network architecture today is characterized by a number of things. One is that it's highly hierarchical and pretty much centralized. So the core network nodes that you can see on the right-hand side sit typically in a handful of sites across the entire country. This, of course, depends on the size of the country. If you go towards the left-hand side, of course, the number of aggregation nodes increases with the next level of distribution all the way to the antenna sites and the base stations. And I will explain why that is important later on when I talk about the future, what the future mobile networks will look like. The next characteristics of the current mobile network architecture is that our mobile core network elements are pretty much hardware-based solutions where a single entity, like a mobility management entity or a packet gateway, will be effectively tightly integrated with a piece of hardware on some sort of monolithic solution from a single supplier. And I will explain later why that is important as well and how things are moving on in that space. The next key characteristic, moving all the way to the left-hand side of the picture, is that our cellular deployments are mostly macro cellular-based. We are starting to see small cells emerging and infill solutions, especially for hotspots and high-demand areas, but there is a long way to go for the types of density and small cell deployment that we expect to see in the future. The last characteristic of today's networks is, again, that also on the radio side, our solutions are fairly monolithic. And what we mean by that is that the baseband units and the radio units and the processing capacity required to schedule the resources for the radio network all come from a single network on what we might call a black box solution. And again, I will explain later how we're influencing industry to move away from that. If I now move on to what our target architecture looks like, as you can see, is quite different from the previous picture, and I will try to highlight the elements where it differs. The first one is that rather than being hierarchical and highly centralized, we expect the compute capacity to be highly distributed so that we can make dynamic use of compute resources and capacity when it's needed and where it's needed. The second one is the need for our transport network to be highly programmable so that as we use compute capacity from different parts of the network, the connectivity between those compute resources can be dynamically reprogrammed to provide the capacity, the speed, the quality of service, or whatever characteristics a particular service requires. The third one is the virtualization of the network functions. As I was explaining earlier, today, so traditional solutions have mostly been hardware-based, which means that the hardware solution and the actual function come from a single vendor. In the future, what we are expecting is more and more functions, and this is starting to happen today in most operators' networks. Network functions will become software components that can be dynamically deployed on general purpose compute hardware platforms. The fourth area where our ambitions differ from today's architecture is that we want to push the architecture to be a lot more open, with open interfaces between the different components and highly disaggregated architectures. And I will come back to that later and explain why that is important. And the last piece, which I will come back to later on, specifically in areas like radio, is how we see artificial intelligence playing a key role in the way we manage our networks in the future, to the extent where we are expecting networks to be increasingly automated end-to-end, thanks to the emerging AI-driven technologies. Now I will move on to a bit more specifics on the radio access network technologies and some of the key challenges that we need to overcome. These are not new challenges, but they are increasing as I said earlier, the capacity required is increasing, and also the flexibility that we require to serve all those different services increases as well. On the one hand, you probably all know that the radio access network is pretty much bears the highest cost base in a mobile operator's network. The actual percentage will depend on a specific operator's network deployment model, but as a rule of thumb is pretty much bigger than the rest of the operator's network costs combined. The second big challenge is that, as we all know, spectrum is finite. And yes, new bands are starting to become available, especially in the high end of the spectrum, in areas like millimeter wave. However, as we all know, those suffer from significant challenges like propagation challenges, as well as obviously coverage and the requirements for line of sight visibility for them to be usable. I will come back to some of those challenges and how we're exploring ways to overcome them. The third one is the high dependency on the physical environment, and this is pretty much the channel between the antenna and the end device. And again, we are going to come back later to some of the ongoing research to try and help with that particular challenge. And the last one, as I've mentioned earlier, is that service differentiation is increasingly key if we want to target all of those new use cases that industry aspires to provide. One of the first areas where we are actively exploring and pushing industry towards our target architecture is the disaggregation and the virtualization of the radio access network. This means that, as I was saying earlier, what has traditionally been a single vendor, you might call proprietary radio access solution, where the antenna, the baseband, and the management plane would be all provided by a single vendor. We want to move to a fully disaggregated model where we can effectively split up the functions of a base station from the radio unit onto a distributed unit, which can be separate from the centralized unit. And we have an important element called the Run Intelligent Controller, or RIC, which I will come back later, as well as the management plane, which can also come from a different vendor and be deployed in a bit different part of the network. This disaggregation provides two main advantages. One is the ability to introduce smaller suppliers, new entrants, smaller vendors who might be dedicated to one of these layers, if you like, in the architecture. So we no longer need to procure our entire systems from the same supplier base, but we can introduce innovation in different parts of the architecture. The second key advantage is that these units can actually be located in different parts of the network. I was explaining earlier how we expect our network to become more distributed and the compute capacity being distributed across the network. So you could envisage having your centralized units for multiple base stations co-located at a particular site, which can bring specific optimization and efficiencies in the way we could actually share that platform across multiple base stations, and also share the processing capacity required to do things like scheduling or pre-coding across multiple base station sites. There are a number of opportunities where we are already exploring the use of disaggregated architectures, such as BT's neutral host solution, which is currently being trialed, which leverages a lot of the elements of this architecture to deliver indoor capacity solutions for multiple operators, where more than one operator can actually have virtualized radio solutions on a common compute platform. The second key area of research I want to highlight is the application of artificial intelligence to the way we run our radio networks. At the end of the day, what we want out of our solutions is more and more optimization of our radio resources, because as I said earlier, they are finite and they are very expensive, both to deploy and run, but also being able to offer differentiated services. Just to run through a few of the use cases and the examples where we firmly believe that artificial intelligence and machine learning in particular can help us address those challenges, are things like nonlinear algorithms for pre-coding and scheduling, where we believe that the potential for massive MIMO to deliver much higher spectral efficiencies than what we have today is entirely possible. The top left diagram shows some of our current assumptions, and under certain current assumptions, what is our expectations to the increased opportunity for using optimal pre-coding, which is the purple line at the top, versus the types of spectral efficiencies we're getting from today's MIMO systems. And as you can see, there is an awful lot of opportunity there by improving pre-coding and scheduling algorithms. As we said earlier, we can actually get a lot closer to that target spectral efficiency that we can see there. Closely coupled with efficiency, again, and optimization is the ability to apply machine learning to things like smart interference management, to optimization of broadcast beams. It can also be used for channel estimation and detection, and it is increasingly being looked at to manage the way we manage energy more efficiently on our base stations, which again is suboptimal today. Another key area, which is closely coupled with the use of AI and some of the techniques and the areas that I've mentioned earlier, is the evolution of radio architectures. There is an awful lot of literature out there and a lot of work in the research and academic environments in the evolution of today's networks, which are highly centralized. Effectively, one antenna is serving a particular cell in a particular area, moving all the way to what they call distributed massive MIMO is one of the generally used terms, where we're expecting cooperative pre-coding to enable us to form service clusters to simultaneously serve users from more than one antenna site. As you can see in that diagram, the three pink antenna elements from each of those could actually be used by cooperative pre-coding to serve a particular user. Going even beyond that concept, there is the concept of user-centric, cell-less massive MIMO. And that's going also using distributed massive MIMO techniques, but in this case, a particular user could be served by three antenna elements from three particular antennas, and a separate user could actually form a different cluster of different antennas. So in a sense, we're moving away from cellular systems whereby every user within the coverage area of a cell will be served by a particular base station, onto a much more cooperative environment and dynamic environment where users can actually be dynamically served by a different cluster of antennas. Of course, there are significant challenges to be addressed in order to achieve that goal. In particular, what the requirements on the front haul network to enable this massive cooperative system to work correctly. Another very interesting area of research that many of you may have heard of is the area of intelligent reflecting surfaces. In essence, what they are trying to overcome is the ability to reflect signals using a diffusely reflecting elements, which could be, for instance, placed in the facade of a building, which could be used to reflect signals in a particular way and in a particular direction. In particular, what is being looked at is how, if you look at the area of active reflecting surfaces, you can change the state of those antenna elements, or those reflecting elements in this case, to actually decide. You could be changing the phase or any other characteristics to actually form a beam towards a particular user or direct a signal towards a particular user. And again, this is in tight coupling and cooperation with the main antenna. And of course, you can then achieve much further coverage and be able to reach your users much more effectively. Now, obviously, challenges again that need to be overcome is to enhance our channel estimation abilities, and of course the protocols for information exchange and phase tuning. And again, we strongly believe that AI is an area that can help us overcome those challenges. But the size of the prize is the extension of the range, and obviously the expected improvements in spectral efficiency and how much capacity we can deliver with our radio networks. In the interest of time, and because I'm sure that you heard a lot about quantum computing, I wasn't going to talk about this in too much detail, but there are probably two areas where I would like to just point that, again, quantum computing can also be very relevant to wireless networks. On the one hand, the use of atomic clocks to massively increase the ability to synchronize multiple antenna elements, and in particular in distributed MIMO systems, as we mentioned earlier. This is particularly important because there is an increasing need to have tight synchronization between highly distributed antenna elements. The other key area for us in, again, a mobile or a wireless environment is the ability to exploit quantum computing for network automation purposes, which, as I said earlier, is one of our ambitions for the mobile architecture. And I just wanted to close the presentation by saying that the size of the prize, the types of services that we're trying to achieve are well beyond just cost savings or trying to deliver more traffic to our customers. As I said at the beginning of the presentation, mobile industry has an ambition to address many different customer segments, many different vertical segments. You can see here examples, and we are very active in many of these. Smart agriculture being a key one, health, as I mentioned earlier, whether it is remote diagnostics, whether it is health monitoring, whether it is IoT enabled health, is another key area of interest to BT. And I'm not going to go through the entire list here. I'm sure a lot of these will be familiar to you. But I just wanted to leave my section by saying we have great ambitions, but also great challenges ahead of us. And we're convinced that the research community, most of you in this audience, are key to make that happen. Thank you very much.
Great, thank you, Maria. As fascinating as ever in terms of the topic of 5G, I think this is probably one of the most dynamic areas in the telecommunications industry at the moment, in terms of the art of the possible and so forth. Lots of activity going on in this area. So this brings me on to the next speaker. So I'd like to introduce Dr. Frank Mullany from Nokia Bell Labs. He's the end-to-end communications research strategist. Now, notice from his bio, him and I have one big thing in common, and it's about how does, the linkage or the connection between how innovative research, the impact it has on the real world. I'm a very practical guy. So there's all this innovation and research is all well and good, but, what purpose does it serve? And such. So the synopsis of Frank's talk is about why can't wireless hardware be more like software? So Frank, over to you.
Thanks very much, Mike. And really what I want to bring to bear here is about 20 years experience in the industry looking at these innovations coming through from research and seeing how much of it actually really got adopted, and then drawing from that some conclusions about directions for the future. And where I want to start with is in the domain of wireless, of the software for the wireless systems. And if you look at the progression there over the last, let's say, 5 to 10 years, there's been a remarkable transformation towards this idea of a programmable network, whereby we have virtualized the functions. We've then introduced the concepts of software-defined networking, network function virtualization in the domain on top of VMs in the NetC in the NetC Mano type of context, and then making it a little bit less cumbersome, a little bit easier, more practical, leveraging the technologies coming from the web scales in the cloud world. We've gone cloud native, or we're starting to go cloud native now, introducing Kubernetes, all aiming towards this idea that in the software domain, at least, that we can do this idea of network slicing, creating a virtual network instances for different applications and providing network as a service upwards. So a highly flexible, scalable type of solution, highly customizable, really economical. That's where the software in telecom networks has gone. What about the hardware? And there's what comes to mind immediately is that song in My Fair Lady, where the two rather misogynistic middle-aged men with plenty more means and more money than actual needs are asking the question, why can't a woman be more like a man? And it was a lampoon of a song, and I sometimes feel that way when people ask the question, why can't hardware be more like the software? And what I want to do is to go back and look at the fundamentals, see what has and has not been achieved over the last 10, 20 years, and point, therefore, in directions where we can go in the future as to how to achieve a higher level of flexibility and adaptability on the hardware side of things. So let's first look then at the drivers. Why is it we want more flexibility in the hardware and on the wireless side, particularly on the infrastructure, the RF and the baseband? Well, on the baseband, we'd like to have greater waveform flexibility to be able to handle all of those new schemes that Maria was talking about in the distributed MIMO, a massive MIMO world, and then the various collaborative schemes that we have there. On the RF side, we want to be able to exploit a wide range of carrier frequencies, different bands, whatever we can grab a hold of to aggregate spectrum together to actually create and support larger bandwidths. And we want to be able to handle the huge diversity of the deployment scenarios that we're dealing with now. You look at where a typical small cell base station can end up in. Is it inside a suburban area supporting smartphone users, or is it in the middle of a factory floor supporting robotic communications? Again, huge diversity there. So, ideally we would love to have a much more flexible hardware. But at the same time, there are a number of anchors that we're dealing with, pulling us back and holding us there. We've limited those same limited spectral resources. When we have spectrum, we want to be as efficient as possible in our usage of it. We want to minimize power consumption. We want to maximize the number of devices with the same silicon. So we have things called standards, and this is one of the key characteristics of wireless communications, is those well-defined standards between the terminals and the infrastructure. And that sets markers, and it sets down the limitations of how far and how flexible we can get. The other one, which crops up in this world of cellular communications, is the need to support mobility. You look at the difference between a cellular air interface and, let's say, Wi-Fi. It's hugely more complex, and a lot of that is about being able to support the fact that your users move around a lot. Some of them move at high speed, and being able to support that requires a high degree of complexity in the protocols and the signaling that we have. These are all challenges which hold us back. But I want to dive into a little bit more detail there, particularly on the RF side, because as well as some of those anchors there, those anchors end up basically defining how far we can go. And you look at what we have achieved over the last 20 years. There's been certainly in the academic community, there's been a lot of research into areas around software-defined radio, SDR. Then the next big buzzword was cognitive radio. We've had in the RF domain, agile RF. But really the things that actually succeeded were driven by very specific needs. So the self-optimizing networks for small cell networks, where you have too many base stations to manually configure. You have VRAN splits because you want to scale up your baseband software. You have things like CBRS in the US, where you're accessing spectrum at 3.5 gigahertz on a shared basis. So you have to be a little bit more adaptive in terms of the way you manage your RF there. These are the kind of things that really took off, whereas the more broader, expansive visions were actually held back. And, if you dive into the detail, you'll find that this comes back to the basic physics of what we're dealing with here. And what I'm going to do is take you through 3 different elements on the RF hardware side and just show you how little room we have for maneuver and how when you try and increase the flexibility, you run into trouble. So as I said earlier, once you've spectrum, you really want to try and pack things in, and that has led to some extremely stringent requirements on the front-end filters that we've had. Classic example being the FDD and TDD bands in 2.6 gigahertz for 4G. The two are really right close up together, and as a result, the transmit filters for both systems had to have really sharp roll-off. If you want sharp roll-off in filters, that applies high-quality resonators and filter structures. If you want high-quality filters, then with low losses, then you have to move back to some fairly old-fashioned 30-year-old technology like coaxial filters, where you have air as your dielectric, extremely low loss, and then aluminium then as your conductor, again, low losses. Now, if you want to introduce tunability into that, that's when the wheels start to fall off the wagon. Because to introduce tunability, the typical approach was to insert a tunable component into a structure like a coaxial filter. And to get maximum range or variation in your behavior, you had to put it in where the electric fields were at their most intense. Now think about what you're doing. You're putting a tunable, often nonlinear, variable component into where you have most of your energy. And immediately that led to significant losses, and your Q factor starts to drop dramatically, and you're no longer able to meet stringent requirements. And this has been a tension that has been really dogging this whole space for multiple years. It's a real challenge to try and deal with this. Another example of how the physics tie us down is in the area of antenna technology. So again, tight frequency reuse, let's say in the spatial domain this time, that means you want tight beams. Tight beams means you need high gain. High gain implies you need a large aperture you illuminate a large aperture, and the bigger the aperture you can illuminate in your antenna structure, the tighter your beam gets. And the way we've done this traditionally to get those large apertures is to create an antenna array. So you don't have just one element, you have multiple elements. Now, the thing here is the design of those antenna arrays has a very, very tight connection with the operating frequency. So you want your elements to be spaced at a certain number of wavelengths apart, and therefore if you want something like frequency agility to capture all of those frequency bands, you immediately have a problem because your physical structure here is confining you to particular choices of frequencies just by the very physical design of things. So, again, another constraint. The third one is in the area of power. And one of the big approaches that has been used over the last number of decades to try and improve the agility of our wireless hardware has been to try and eliminate the RF hardware altogether by moving the digital interface from analog to digital as close as possible to the antenna. And, this is a core idea behind a lot of software-defined radio approaches. The issue there is as soon as you move into the digital domain, you have quantization and you have time sampling. And you compare that against what you can do with analog processing. In analog processing, you're in continuous time and you have a much higher degree of precision effectively in your variables. And as a result, you've got a much more efficient, from a power perspective, a much more efficient structure for actually manipulating and processing signals. So the analog domain is very difficult to design in. It introduces noise, interference, all kinds of problems that are difficult to handle, but it is efficient from a power point of view. And that has been always one of the things that has dogged more software-defined approaches. Okay, so I've listed a set of bad news stories here for the last 3 slides. Are we dead in the water? Well, no, not quite. The actuality of it is that if you actually embrace the reality of the physics that you've got behind it and really take that on board, there are always ways around this problem. And this is where I've had a great time working with research teams over the last, a decade or so, is finding those ways of rethinking the problem and then having breakthroughs in terms of getting the kind of agility that we're looking for. So when it comes to antenna arrays, the key thing here to remember is it's not actually arrays that you need to shape a beam. Yeah, that's one way of doing it. You illuminate or excite the medium at a number of distinct points. But really, what you have at the end of the day on a tower is a particular surface area, an aperture. And that's what you really need to play with in terms of your structures to shape the beam in the way that you want, but not to lock yourself down to the actual physics of a particular wavelength. In terms of filters, one of the approaches that we've found that has worked extremely well is to move away from components, tunable components, but to look at tunable media. So what we've been looking at inside Bell Labs has been looking at materials with good loss characteristics, but who, in their bulk characteristic, have ways that can be tuned to have different properties in the RF domain. And what we've done is we've looked at areas such as electrochromatic materials. The other one that we have is dielectrophoretic materials to find and create tunable solutions that don't act on the overall field and the overall device, rather than on a single point inside the device where the electric fields are at their highest. So to try and get to bulk tunability. Again, on the power problem, one possible way forward here, and it's a challenging one, would be to look again at the world of analog computing paradigms, so as to try and combine that flexibility of digital with the efficiency of the analog world. So there are approaches to deal with all of these, but you have to work with the physics, not against it, to achieve the aims of what you're trying to get at. Okay, I want to spend another couple of minutes now looking a little bit at the baseband processing. I'll move a little bit away from the hardware and just look a little bit at a few trends of the baseband processing as far as agility is concerned. And because there's a particular story here I want to pick up on. And if you look at the world of baseband processing, one of the trends that has become very apparent is that we have quite a wide variety of hardware paradigms now in our baseband solutions. Whereas, let's say 10 years ago, you're looking at ASIC or a bit of DSP. Now you've got FPGA, graphic processing units, DSP, CPUs, a whole lot to a full range. And that arises really to better targeting of the hardware infrastructure at a given, for a better matching of the hardware solution to the particular type of processing that you have. So, inside a processing chain, we have a huge variety of processes, whether it be equalization, simple detection, decoding, high-level protocols, etc. And you have to pick the right type of hardware structure to be able to deal with it. Now, the interesting one here is the machine learning one in the middle, and it's the only one without an acronym for a good reason, that real-time inference down at the baseband processing side is a pretty new area, so we haven't quite got a good acronym for it yet. But the idea of real-time inference engines is quite an exciting new space, and there are a couple of reasons for that. But let me first talk about how it's likely to develop over the next couple of years. At the moment, we're starting off with, let me just check again. Yeah, sorry. Yeah, so we're starting off whereby at different points in the receiver in particular, we're going to introduce machine learning algorithms and solutions. And that's going to gradually over in time encompass the entirety of the receive chain. That's likely to happen over the next 5 to 10 years, or at least bigger and bigger portions of the chain. In the longer term, the interesting question is, what if we apply the machine learning problem to both the transmit and the receive side. Now that implies some level of negotiation between the two as you go through the machine learning mechanisms to converge on the correct baseband solution. That's kind of the long-term aim where the industry may end up heading towards. It certainly would be a radical change. I suspect it will take quite some time for us to get there to that level of vision. Certainly it's something that may appear in the world of 6G. But the interesting question is, why would we go to that bother? And then there you have to come back and see what the value drivers are for this at the end of the day. And fundamentally, you can see them there at the bottom. The first one is this idea of being able to deploy a solution to multiple different scenarios with a single product. So you will allow the machine learning to adapt to the scenario into which you deploy. That implies as well, though, from a development standpoint, the way that we design and develop these individual components inside the transmitter and the receiver will look very different. So we end up with a generalized structure that learns in the field, so we don't actually necessarily design to optimize a priori. So we have a very simplified development cycle. Then when we get it out there into the field, then we have something that adapts to the particular situation you're in. And ultimately, really what we're aiming for is to be actual to deliver the performance that the end user is actually requiring. But the bottom line here is that when we introduce machine learning, it will be driven by needs in terms of what we need to see in the field. And that's one of the other fundamental messages I want to give through here. When we come back to that question, why can't wireless hardware be more like software? The real answer is, why should it be? And once you have the answer to that question, you can go back and really make the decisions as where you have to put the effort in to get the flexibility that you want, whether it be in the baseband with machine learning or in various parts of the RF front-end chains up front. And that's the challenge that we face, to try and match that need with the physics and with the economics. Bring those three together and you get the sweet spot for increased flexibility in the systems that we deploy in the future. Okay, thank you very much.
Great, Frank. Thank you. Thank you very much. I was just looking at your photograph there, and I noticed that yesterday we had a Strictly Come Dancing reference in one of the presentations. And within this presentation alone, we not only had a Star Trek reference for those of you old enough to remember it, but also had a My Fair Lady reference as well. So I'm going to start a reference bingo sheet. So great, Frank, thank you very much. So our next speaker that I'd love to introduce is Professor Robert Pachaki. Robert is a professor in the School of Computer Science, Electrical and Electronic Engineering, and Engineering Maths at the University of Bristol, and he's also a fellow at the Alan Turing Institute. And so on that note, Robert, I'd like to hand over to you. Thank you.
Thank you, Mike. Hello, everybody. It's really good to be with you. Now, I don't have any references to movies, but I do have references to computer games. Right. So the title of my talk is Wireless Systems, Self-Driving Vehicles, and Digital Twins. So I'll attempt to straddle all those areas, and I'll try to pick up some areas of overlap. I've just looked again at my slides. I don't mention AI anywhere in the slides, but there will be undertone of AI across the board. Okay, so I will start with the concept of digital twins. Digital twins is one of the hottest topics that is currently around. I'll try to make a case why this is becoming even more important as we go along for wireless systems or connected automated mobility and many other disciplines. Here I've picked up a definition by IBM. I'm not going to read it. I just want to point a few keywords in there that I think very succinctly describe what's the key idea here. It's not just a mirror of a real system. It's essentially an object, a living object that lives together with the real object, evolves together, and acquires the features of the real object. So here's very brief history of the digital twins. All I want to say is, I guess that's not going to be too surprising to you, is digital twins do not represent a revolution. It's more of a evolution. And it all started in sort of 1960s, whenever compute resource was available, or compute resource was available to do some fairly decent computations. Over the years, it progressed slowly. I pick up here a few milestones on the way. It's interesting to note that the term itself, digital twin, appeared in the published form in early 2010s, but it traces back to 2004. Apparently, was used in the presentation. And off we go to the current day, where the Gartner lists digital twins for the last 3 years as a top 10 technology trend. So you can be sure we are hitting the hype, top of the hype curve. But what I want to say is there's a good reason for that, and hopefully I'll show you something slightly different. Before that, just quick slide to show where these ideas have percolated. There's a number of engineering sort of verticals, sectors, that you will not be surprised that you will find the digital twins there. But you can also find it in a medical domain. You may have heard there's a big European project called the Human Brain Project. But there's also many other smaller, less known projects that attempt to build digital twins of various organs, for example, heart. But what I really want to argue here is slightly a different approach to digital twins and why they may be useful in our research and development of wireless systems. Right. So the reason is that we have currently a bit of a problem with machine learning, with AI. AI, machine learning, is making, it's been mentioned in the previous talks, and there's a good reason for that. The current crop of techniques really is at least success stories are supervised learning techniques, where it's still great that we can use them. But the trouble is that with most of the real world data, the data is not suitable to be used with supervised learning techniques. The world is full of messy data, unorganized, uncurated, and unlabeled. And many companies go to great pains to label the data. To quote one example, Tesla, when developing their own autopilot, the team of labelers is about 10 times as big as the team of machine learners. So it's a huge problem. So real world is messy. Now we could try to do the old way, crack the fundamental physics, develop solutions, find E equals to MC squared for your problem. But again, the trouble is the world is too complicated to do that analytically. What's left? Well, develop better machine learning strategies, better AI, and indeed the community is pushing exactly in this direction, and there is no effort spared in order to develop new techniques, new self-supervised learning techniques, unsupervised, but in essence, this is still in its infancy. I should signpost there are some success stories. For example, in NLP, natural language processing, GPT-3, you may have seen in public domain. It's great, and that's an example of a success of self-supervised learning. But what I want to argue here is that digital twins can actually step in and provide this kind of bridging technologies. So while we're still waiting for this amazing self-supervised learning, unsupervised learning, which who knows how long it will take, we can use digital twins in the meantime. And here's one example of why that strategy works. And in fact, there will be some other niche applications where it will always work. So here we have Alphago example. So here's my computer game example. And in my mind, this is an example of digital twin. Again, I'm sure most of you would have seen press reports about 3-4 years ago. AlphaGo beat Lee Sedol, the champion of Go, the ancient Chinese game. I'm going to talk about here a newer generation of that version. So specifically AlphaGo Zero. So AlphaGo Zero is a later version, and the difference is that whereas AlphaGo, the version of Lee Sedol, was trained on many, in fact, thousands of games of Go that were fed. So essentially, loads of data from human-played games were fed into the algorithm to pre-train it. AlphaGo Zero did not use that. AlphaGo Zero starts from scratch and achieves amazing levels of performance. It did not make much news. I think it's simply because, it's very hard to show it. There are no humans left to be beaten. AlphaGo Zero could only beat AlphaGo. But here, the main kind of message take home I wanna say here is this is an example of turning computations into data. We don't have good labeled data, but we can use computations to make up for it. Labeled data is expensive. Computations, on the other hand, are becoming cheaper and cheaper. I've got here on the right-hand side is a bit of a schematic of this algorithm. I put it there because I could not resist. It's a marvel of an algorithm, but obviously we don't have the time to go into details. I just want to say that AlphaGo Zero is a beauty that links together deep neural networks and kind of more traditional search-based techniques, kind of multicolored tree search on the top and a neural nets at the bottom. And it's absolutely amazing stuff. Another example I'd like to put here is, self-driving vehicles and how digital twins are used in connected and automated mobility. So I'm sure you've seen in the news, Waymo is out there testing their vehicles. What is reported less often is the fact that Waymo is actually doing much more tests in software, in essence, in a digital twin. And in fact, Waymo recently admitted that during COVID lockdown, they did 20 million miles a day, which is about equivalent to 100 years in the real world testing. So overall, so far, Waymo has done 20 million miles on the roads and 15 billion miles in digital twin. And the reason why you want to be doing a lot of that stuff in software is because, in fact, it's very difficult to learn from the data acquired from real life, especially in kind of a safety-critical application like automated vehicles. Most of the miles you clock on the real world are actually boring miles. Nothing ever happens. If nothing ever happens, you don't learn anything. You do not adjust the driving policy because there's no point. What's interesting is all the edge cases, all the kind of difficult situations where you may not have seen before. So digital twins are super useful for that because what you can do is you can attempt the data augmentation. So you use your real live data, but you can manipulate. You can add vulnerable road users. You can introduce this kind of pedestrian that would want to jump in front of you, or erratic cyclist, and the rest of it. And also you can obviously validate and test in new software. This is a just very small plug for the work we have done in this space. It's a project called NGCDI, and we developed digital twin for wireless, so specifically wireless network, also within the vertical of connected automated mobility, but taking a bit of a zoomed out view of this. So rather than developing a driving policy for one vehicle, is how you manage entire fleets of vehicles, how do you make sure that all these vehicles get the digital service in there. Another area I want to signpost is the softwareized future versions of wireless systems. Maria, in her presentation, made a very good case where we are headed in this direction, why we want softwareized, disaggregated new networks that will deploy Open RAN techniques. And Maria also mentioned several kind of examples of what that policy might be to run your Open RAN, and also real-time control techniques such as beam management or interference or this type of techniques. But what I want to say is you can also test, once you have digital twins, you can also test stress test. So your network, look for the weak points, and this could be due to the internal factors such as anomalies within the system, and maybe external intrusion, so IDS detection. And furthermore, it's actually becoming, you can see the confluence of the idea of digital twins and Open RAN. Open RAN, again, that's been said already, essentially that means software on a COTS, on a commercial off-the-shelf device. So once your network is running that, there's no problem to duplicate. It's just a software. You make another copy of the same software and run in a slightly different place. It's different instantiation of the same thing. So the digital twin becomes very easy to be hacked. And there's one more example I want to show. This is what you can do. Again, this is an attempt to answer the kind of ever-present question when various people are looking at connected automated vehicles is, will it be any better? What will be the benefit? And here's just one study. Again, I'm not going to go into details, but essentially the task or the question we asked was, is there any benefit in terms of traffic flows? If you have three groups of vehicles, so HD here is human-driven vehicle, AV is automated vehicle, CAV is connected and automated vehicle, is what are the differences if you have these three classes? And maybe I'll just quickly say what are the assumptions behind the simulation. Human-driven is what it is. AV assumes it's sort of similar to human-driven, but it cuts the reaction time. So we can assume, you remember from your highway code, you should keep 2 seconds distance to the vehicle in front. 1 second of that is due to reaction time. Automated vehicles have basically 0 reaction time. And connected automated vehicle add the increased perception field. Through the wireless communication, they will be much more aware about the state of the road in principle, for 100 meters and kilometers ahead. So they can continuously replan the road. Okay, this is just quick slide. Yes, I should have warned you this would be a little bit geeky, but well, we're all geeks, so perhaps no need to apologize. This is just a numerical representation of how these systems would work. For this particular case, I'm not making any claims. This is the ultimate result. This is just a glimpse into this new world of future connected vehicles. We've picked up several cities. These results present only 3 cities, but what we want to show is connected automated vehicles can achieve a better average speed. So essentially, the traffic flows a little bit smoother and faster through the city. That's another quick area I want to mention is anomaly detection. Again, you need your digital twin if you want to test your anomaly detection systems and develop in principle, you can use unsupervised learning techniques, and that's in fact what is being done in this study, but also by many others that have done similar studies. But in any case, at the end of the day, when you want to test how your system is picking up anomalies and IDS, so what you still need to know whether those have been picked up correctly or not. So you need to have a label at the end of the day for the testing stage. So again, in real world, this is really hard to develop anomaly detection, looking just at the real world data. In the digital twins, there is no problem. You can always inject and stress test any anomalies you want. This beautiful butterfly slide here, it attempts to show one technique that is being developed recently in AI machine learning called Autoencoder Network, which essentially takes the inputs on the left-hand side. This, you may recognize, this is Bristol, in fact, or rather roads of Bristol, roads layout of Bristol, and it tries to learn compact representation through this kind of squeeze in between of this butterfly network. And the idea is once we have a compact representation, we can then pick up anomalies, those that are look outliers in this compact representation. And that may be my final geeky slide that attempts to show that this strategy in fact does work. It is in principle binary hypothesis testing problem. So you know we have this situation where we want to trade false positive rates with true positive rates. So we want to minimize false positive rates, maximize true positive rates. You want to get curves that look kind of a little bit like square, so they'll go steep pretty quickly, and the area on the curve is maximized. So here what I want to say is standard techniques that are represented by this yellow and dashed lines. Dashed is actually it's a random decision. It's as worst as you can have. Yellow is state of the art, and a blue one is this new technique that is based on deep neural nets. And this is my, I believe, my final slide, where I want to point to yet another application. I've sort of alluded to it as I was going along, but I think is another important application where, well, we know that our networks, as we race towards these new techniques, we pile on all sorts of layers of software, or open run, and everything else. There is, in fact, the network gets complicated in the architecture. Are we sure that it's all watertight? It's not exposing any vulnerabilities in the process? And the answer is, well, we cannot be really that sure. We're doing our best. You know, this is we are building in security from start, but you know, there's this residual thought that things may be left unchecked. And one way we can use your digital twin is to check for vulnerabilities in the network. And you can do two things at the same time. You check for vulnerabilities and plug the holes that you may have found and exposed, all in one go. And you can set it up as this adversarial game, where what we have is on the left-hand side, you might have malevolent agent, you know, the bad guy that attempts to bring your network down. And on the right-hand side is the benevolent agent that attempts to counteract this. And you set it up as a game. One thing that I think should also be clear is that the future bad guys will not attempt crude attacks. They will also use state-of-the-art AI. That's I think this should be absolutely clear. So the only way to counteract this is to design systems that can spot that automatically, that can themselves think of attack surfaces that cannot be thought by a human. That's one way to achieve this. Okay, I've got one more slide. I just want to say a few words. Is it all that rosy? What are the challenges? Well, there are still challenges. One thing that you may have predicted is that digital twin needs to be a very good representation of the real system. Okay, so to make some predictions to learn, you need to have your twin as good as the real thing. And as I mentioned, in some cases, actually, that task becomes easier and easier. Open Run is one of those areas, because you can make a twin with one press of a button. You still need to model your real world aspects of it. So propagation and the rest of it. That still is a challenge. But we've been doing that for many years in wireless community. So we should maybe not be petrified about that aspect. And I want to point out, what happens if you don't have the ideal twin? There's another few interesting areas that are happening in machine learning that can also come to rescue. And one is called transfer learning, and the other one is called the meta learning. And the idea in both cases was a similar idea, but what we hope to achieve is we want to have a situation, a twin, that will be able to be adjusted, tweaked, with just the minimum amount of well-curated data from the real world. That's essentially the idea. So, if we design our system well, and it can be refined in a very clever way, that's really good news. And that is my last slide, so thank you. And yes, I want to just give a shout to BT EPS as in Innovate UK for sponsoring some of the work that I have presented.
Great, Robert. Thank you. Thank you very much. So, once again, fascinating discussion around the whole digital twin thing and the use of AI in this particular space. So, if you want to stay with us, so at least leave your microphone on, and then Maria and Frank, if you want to turn your microphones back on, we'll move into the panel session. And this is where I get the privilege of asking you some really difficult questions, hopefully, from that perspective. And I'll start with kind of a generic one, and I'll go to Frank first with this. But there's 5G is quite clearly kind of a game changer. It could be a game changer in so many industries. Lots of re-engineering going on behind the scenes and such. But in my head, there's this kind of elephant in the room around 5G, and that's low Earth orbit satellites. So you got a number of companies throwing LEOs up there that can do high bandwidth, can do low latency to a point. So I guess, Frank, I'll go to you first. Do you see LEOs having an impact on this wider wireless community?
I think the game has moved on in the urban environments and in the indoor environments for LEO. Where they may have an impact is in terms of some of the rural scenarios and being able to get a high bandwidth, high throughput in rural setups in a manner that would be uneconomic otherwise. That's potentially, I think, the sweet spot there. But if you look at what's going on in the cities, our cells are getting smaller. They're going indoors. They're not spaces that LEO will play in, ultimately. But we still have that outstanding challenge of how do we get super high bandwidths out into broad areas in rural scenarios at still an economically tough, challenging space. And perhaps that's where I would look at LEO.
Great, thanks, Frank. Maria, do you have a view on that one?
No, I completely agree. There is a view that these systems can be complementary.
Okay, great. And Maria, you may want to turn your video off again because your audio is breaking up on us again. I'm afraid. Great, but thank you. So, Robert, a specific question for you. It comes from Chris Ewan. Self-driving vehicles. Has digital twins found the cases in the past that have caused fatalities? Now, has it found weaknesses or potential fatality scenarios that have not happened in the real world yet?
Well, it's difficult to say about fatalities in digital twin. That's the whole purpose of it is to develop systems that will learn and react so that fatalities in the real world are averted. Yes, it's a huge challenge. I don't want to say it's all kind of happy and dandy that we're gonna progress with this. what I wanted to show and say is there's no way we can do enough tests in the real world to de-risk the situation. The vast majority will have to be done in software. And once the systems are super ready, the kind of extra mile can be done in the real world.
Okay, and I guess the fascinating take on that one, because they was asking also if the models have predicted any scenarios that haven't happened in the real world yet. Have you come across any of that in your research?
All right. Okay. I would imagine that yes. I don't have sort of insider view to the output of the simulator of Waymo. Waymo and all the other companies are very, very cagey. But yeah, I would imagine this is happening. They've covered so many more miles in software that they must have encountered. In fact, the software was done specifically to encounter all sorts of odd cases. And it's better to build a system that can react, be overcautious. They can deal with all sorts of weird situations, hoping that the real life situations are a subset of what was tested on.
Okay, great. Thank you. And one of the first questions we had come in comes from Simon Newhouse. And Maria, I'll start with you on this one. But is anyone doing any research into mesh networking between user devices?
Yes, absolutely. Mesh wireless technologies, not a new thing. There's been quite a lot of research for a number of years. In the cellular space, there's been quite a bit of traction with regards to what they call device-to-device communications, and increasingly what they call V2V or vehicle-to-vehicle in the context of the automotive industry. I would say it's not, none of those areas have really taken off. There might be some specific use cases where we start to see the emergence of mesh or even device-to-device technologies being implemented. But the answer to the question, I suppose, is yes, there is a lot going on. I suppose not so much in real life or in real implementations just yet. I don't know if Frank has anything to add to that.
Actually, again, I would have pointed to exactly the same use case, the vehicular-to-vehicular one. And again, for coming back to the earlier question around safety, it's driven by that, the need to be able to do platooning of multiple vehicles. And keeping the latency of the communication down between the vehicles. There's a strong driver there for doing device-to-device comms. But you do need that kind of a driver to actually justify that, because the challenge about mesh communications is that you're using resources of another device to get to what you want to do. So you really want to have a strong reason for the devices to collaborate. Vehicles is one good example. Sensor nets are another one, where in the low power domains, where you want to try and get messages from one end to the other end of a sensor net with the minimum amount of energy consumption possible. That's another space where there's a strong driver for that kind of collaboration. When you've got those use cases where that collaboration is needed, that's when mesh takes off. Where you don't have that kind of driver, whether that isn't that strong reason why you need to collaborate, then often centralized architectures tend to be simpler and more cost effective.
Great. Thank you. And I guess, Robert, we've had a follow-up question on the autonomous vehicle thing. I said, would it be fair to say that there are more fatalities caused by people than by autonomous vehicles?
Yes. Currently we know that the statistics are 95%, I think, around accidents are due to the human error. But again, we hope that the penetration grows, so we can lower that component. So as human drivers are being replaced by machines, then that should go down. but the world where there are no accidents, I think it will be very hard to achieve. So that's something that the industry needs to manage that message very well. So the message from one particular OEM in car that they see a world where the vehicle will never kill anybody. That I think is going to be very hard to achieve.
Okay, great. Thank you. I mean, you can't, whenever there is an accident, you can't help but see the headlines because the press makes a big deal. I love it, but they just don't look at the context or the scale, I suspect, in terms of the number of accidents that are happening. So but it makes headlines, unfortunately, at the end of the day. So, Maria, another question specifically for you says, I watched the DARPA Autonomous Spectrum Management Collaboration Challenge with interest. Do VT's AI-driven radio network systems have similar collaborative capacities? And if so, could you explain?
I'm sorry, Mike. Could you repeat the question because you were breaking up at my end?
Okay, yep, sorry. Sorry, it's fine.
It's my audio connected.
So, Colin Cures has asked the question that he has watched the DARPA Autonomous Spectrum Management Collaboration Challenge. And he wants to know, do BT's AI-driven radio network systems have similar collaborative capacities?
Right. Okay. Yeah. So yes, about spectrum management, and again, yeah, this is not a new topic as we all know, and one that has been researched for quite some time, and again, not quite sure that it's taken off as a concept. It is an area where we believe AI can help. I'm not sure what you refer by BT's AI-driven radio systems, because obviously those are, I suppose, currently in research. It's not like we have got or we claim to have an AI-driven radio system at present. But in terms of is that an area where we believe AI can help, the answer has to be yes. I wouldn't say it's top priority for us at the moment, although it is a very interesting area that we're keeping an eye on. I don't know if anybody has any other thoughts or comments.
Well, I'll come back. I haven't been following the latest work by DARPA in this space in terms of the distributed management solutions for spectrum. My own feeling is that it's going to be challenging for the lower frequencies, because even in spaces where we now have spectrum sharing regulators tend to have gone back to a command and control type structure. In other words, we give you the right, we negotiate centrally for you give you the right to gain access to spectrum, and then you have that right then to use it in this particular area. That may change as we move up into the millimeter wave bands, and we end up with much smaller systems, much more distributed, higher numbers, and again we're dealing with more shared spectrum again in many of those bands. And in those cases, maybe autonomous spectrum management might become the more economic way of managing that kind of spectrum.
Okay. Well, that kind of brings me on to I guess a bigger question around the whole area of spectrum efficiency. So there's a range of technologies being deployed or looking at being deployed in the 5G space, whether it's MIMO, whether it's AI, frequency read, whatever it is. So, and I'll come to you, Frank, in the first instance here. Which technique or which technology do you see having the biggest impact on the efficiency of the spectrum that we'll have allocated to us in this area?
In the 5G space?
Yeah, 5G space, yeah.
Well, in the first instance, I think it's going to be more about the RF hardware, really, in terms of we're now dealing with very new transceiver technologies as we move up well beyond the 6 gigahertz mark. And that's the first space, I think, that needs to settle down and mature for the kind of systems that we have, particularly with mobility, right? When people are moving around a lot and managing that. And then in terms of what happens at the baseband, I don't really have a strong view in terms of what directions we're going to end up going there, particularly as we move up to the very broad bands. And, when we get to 1 gigabit per second or 1 gigahertz type carriers, which we will in the longer term as we push up into the 100 gig region, and it may not necessarily be efficiency be the issue. It may be just being able to feed that kind of data stream through in a power efficient manner might be the critical question. So efficiency might not be the problem when we get to huge bandwidths, right? But I don't have a strong view, to be honest, on the efficiency issue.
Okay, great. Maria, you got a view on that one?
Well, I'm just not sure there is a single bullet, to be honest, a silver bullet, and it's going to have to be a combination. First of all, those technologies, and the ones that you've mentioned, and probably the ones that have been mentioned across all three of our presentations, to an extent, are complementary, and they can be combined to solve different challenges, but also to target different use cases. So I agree with Frank. Not every use case requires the efficiency or the additional bandwidth or huge capacity, but there may be additional requirements to do with the reliability of the system, or, as we mentioned a number of times, the latency that is delivered. So increasingly is having the flexibility to combine the different techniques that we have to be able to serve different vertical industries and different use cases much more dynamically and rapidly also than we've been able to do in the past. So I'm not giving you a single answer. I'm just saying it's actually the right combination of all of the above, if that makes sense.
Yep. Okay. Cool. So I guess Robert, would you have a view on that one coming from your digital twin AI perspective about the impact that some of the work you're doing may have?
I would like to argue that I think even though there's been a lot of progress on AI, there is still much to be done, and we just don't have yet very nice, neat algorithms. In many cases we do, but I'm watching lots of papers that have been published in the last few years, and the tendency is AI everywhere, and specifically deep neural networks. And I think that the future is the kind of very neat combination of more classical techniques. The telecommunications community spent decades developing really good algorithms. So we should not just chuck them away and put neural net in place, but we should try to combine. So the technique that I think recently has been termed as a neural augmentation, that is the term coined by Max Welling, he's a VP of Qualcomm. And I think that's the way forward. It's literally, there's still kind of areas of niche where we cannot crack it. We have techniques around that we've been developing over the year, and we just need to blend them all together. And one area I want to say is the control. A lot of stuff, even though explicitly did not say, is optimal control, how you manage your resources, how you run your network in some optimal sense. And that's one area of AI that is still lagging behind. So reinforcement learning is the type of machine learning that comes to rescue, but it's not providing a full rescue. There's still plenty to be done in that space.
Okay, great. Thank you, Robert. I'm going to pivot here slightly. This is more of a security question, but it's an incredibly valid point, because some of the work I've done with our cyber team at BT. And the basic question is, as with most things that are computer-based in one form or thing, or particularly with vehicles, do you see that with some of the new systems within autonomous vehicles and such, do you think they can be security breached and cause some issues? And Maria, I'll go to you first on that one.
Yeah, sure. Sorry, I thought you were talking about vehicles and you were going to talk to ask the question to Robert, but I can have a go. Mostly from a network vulnerability perspective, I suppose. If that's, I suppose, an element of that question. So yes, our network's moving towards software-driven and even cloud native, as we also refer to the new architectures. Do introduce a set of challenges in the way we secure and overall we manage our networks. They require an evolution of the mindset, even inside the operators, in terms of how we manage the networks of the future. And I'm being more generic than just security, actually. I'm talking about managing the overall network, which includes performance, includes service assurance, and obviously includes security as well. So we are, to be honest, along that journey, and I don't believe we have solved all the issues, and that's why obviously a lot of this needs to be done in a very much a gradual phase where I suppose all parts of the ecosystem are learning how to evolve into this new architecture and this new way of doing things. But you can look at it from the opposite side and say, well, actually, we can leverage a lot of the security mechanisms of the software world and the cloud compute world in this new architecture and apply them, of course, to ensure the levels of security that we require and reliability and performance and all those things. And as I said, it's going to be a gradual journey. It's going to require a huge shift in, as I said, the way we do things and the way we approach those problems, and it's by no means complete. All challenges have not been solved so far, but we're gradually evolving, I suppose, the thinking in that space. But there is no fundamental reason why a software-based network cannot be as secure or as a hardware-driven network. It's just about doing it differently and obviously learning how to do it as we evolve our networks into that new architecture.
Okay, great, thanks, Robert. I'm pretty sure you got a view on this one.
Yes, but I do agree fully with Maria. So maybe just in attempt to add a little bit is I think yes, there's no reason why this networks could not be secured. But I think we also need to have a sort of different approach. In the past, we would try to build, security at the outset, and then hope that it all works. I mean, on occasions, just plug the holes when they occur. But I think going forward, it's going to be an ongoing activity where, the network will be tested and all the time as we go along, trying to discover the vulnerabilities in automated fashion and plug them as we go along. And then, obviously we need AI for this. So, there will be sub-components running in the cloud and continuously trying to do that job.
Great.
Quick thought there. Another role there for AI is in the area of anomaly detection, and the challenge is quite big. For example, if a particular node is getting flooded with data packets, your anomaly detection solution has to be able to decide is this just a valid increase in traffic because of some demand that is legitimate? B, is it a node that is failing and thereby behaving in a weird manner? Or C, is it a malicious attack? So that one scenario, you have to make a decision as to what it is actually happening, because the way that you respond in the network varies hugely for each one of those scenarios. So that's one of the challenges that's with us in terms of securing the networks. The second thought is we have to move beyond the idea of security being just the security of connection. We've got to look at the idea of security of function, security of data, particularly as we move compute functions around in the network and in the cloud and move the data around. All three elements now have to be secured, and that requires a lot more work inside the industry.
Great, thank you. And I've been waiting for this question because every time you talk about 5G, wireless, mobile, 4G, whatever it is, it inevitably comes up in some form. But John Borowski's asked the question, but there's been some controversy in the scientific community about the impact of the 5G power band. What's your perspective? And Frank, I'll come back to you on that one in the first instance.
So there's, 5G gets thrown around a lot. I'd like to distinguish below 6 gig and above 6 gigahertz. Below 6 gigahertz, we're dealing with waveforms which are not hugely different from what we've had before in bands which are similar to what we have in 4G. So is there a big step change there? Not really. What is new is we're now transmitting in up at, let's say, 28 gig, and we're pushing up into the higher frequencies. And I haven't seen evidence for any serious issues there as of yet. But as an industry, we need to do two things. One, we need to continually check, investigate, look at it with an open mindset, just to make sure we're not missing anything. And two, we then need to build our equipment to the standards that are out there to ensure that no issues will arise. And it's very simple. They're the two things you have to do: investigate and build to the right safety specs.
Great, thanks, Frank. Maria?
Yeah, I mean, just to I suppose expand on that. Yes, and we are doing both. We obviously continuously check any equipment before it ever goes into the live network to ensure it falls well below the guidelines. There is actually public checks being performed, and there have been reports by Ofcom recently where we are orders of magnitude below, again, the safety limits set by the regulators, and that's in the public domain. And again, as we continue to explore new technologies, and I agree with Frank, obviously, that the challenges in the millimeter wave are completely different and they need to be tested. Even the tools that we use to measure those power levels have to evolve. And again, we work with Ofcom, and some of you would have seen that there is an Ofcom consultation for a new tool that is being explored to, again, test those power limits. It's all a moving picture, and the whole of industry needs to collaborate and to adjust and to evolve to make sure that we are well below the safety limits.
Great, thank you very much. So, Robert, I'm going to ask you: do you have a view on that one? Are you close enough to that issue?
I don't think I agree with the premise of this question. I don't think there's that much controversy in the scientific community. I'm embedded within the scientific community, and there's not that much backlash. What is certainly the case is the perception, the public perception, that is the problem. And I think that we can, debate why that is and what to do about this. But, that seems to me a separate issue. But, as Maria said, these issues, everybody is very responsible. Nobody will put up something that will not meet, strict safety requirements and norms.
Great, thank you. I must admit, I had a discussion with somebody a few weeks back, and it was going on about just radio in general. I said, fine, how about if we turn your TV off and we turn your radio off and we turn all the satellite stuff off that's up there now? And they go, yeah, but that's different. I'm well, actually, no, it's not. And I think it was the context for some people, because all they see is the news around 5G in the press at this stage. So a couple more questions in the time we've got remaining. Question from Steve Diet. There's been a lot of discussion around the future architecture of the mobile or the cellular network at the end of the day. So how does the current deployment of Wi-Fi 6 and obviously in the future Wi-Fi 7 support and work with these mobile architectures? So Maria, I'll pass that one to you in the first case.
Thank you, and hi, Steve. Thank you for the question. As you would know, there has always been this debate around, is it Wi-Fi or is it cellular, or how can we bring them together? One of the things I would say that BT has been pushing for very strongly within industry is that we really need full convergence of fixed and mobile, okay? And that's regardless, by the way, of which Wi-Fi version you're looking at, although, of course, we know that there is Wi-Fi 6 becoming very strongly positioned as potentially an alternative even to cellular technologies in some deployment models. But as I say, the ultimate game has to be about bringing them together. We have actually worked very closely with Nokia Bell Labs on this call, but and other parts of industry to push that vision into the standards. And again, our ambition is that when a user connects to the network, they don't care or know which access technology they happen to be using at any point in time. The device and the network need to collaborate to choose the best possible access network or access networks. It has to happen simultaneously over more than one access link to provide the quality of experience. Between now and then, okay, we know obviously that there will still be a coexistence model where Wi-Fi is obviously, the proliferation of Wi-Fi devices is not going anywhere, and of course Wi-Fi 6 is being positioned as potentially an alternative in some use cases, as I said, to cellular. We still believe that there is a position for both. BT is very strong on both Wi-Fi and cellular systems. We can either have a selection depending on the particular use case or deployment model required. But as I said, the ambition has to be in the future that the two work in conjunction as opposed to being alternative technologies. I don't know if Frank wants to add anything to that.
Great, thanks, Maria. Frank, do you have a view?
I'm just laughing because Maria and I have collaborated on exactly this question in the past. So there isn't really a huge amount for me to add. I'll just re-emphasize that point that Maria brought up, which is multi-connectivity. If you want reliability, multi-connectivity is one of the best approaches of getting that by exploiting the diversity of access technologies available to you. You can create a high degree of reliability well beyond even what is achievable today. So there is potential for the two systems to collaborate to achieve that. And the other thought is, I know Wi-Fi 6 has been aiming for low latency, which is great to see, but there's still always that value in clean spectrum. And that's one of the big advantages that cellular will always have, is the fact that you have much less worry and much less work to do to manage the interference issues, and that will always have its advantages. There are overheads, of course, in terms of complexity then in that you have to deal with as a result.
Great, thank you. So, Robert, once again, is this an area where you've got some expertise that you can add to this?
No, I think I'll give it a pass. Sorry, not fair. That's not fair. But what I do instead is answer another question I can see on the chat, but it's up to you if you allow me to do that.
Okay. Well, I've got, let's have a look here. We got a number of different questions here. Okay, right. Yeah, well, I've got one more question here, and then and it's come from Bethany Yoshida. It's more of a this is really kind of a BT question to some extent. So Maria, this is obviously going to kind of wing its way towards you, but providing, as we're providing fiber to more rural areas is very costly. Could we use 5G basically as part of a universal service obligation? Is this something that BT is looking at? So this is about 5G in rural areas, basically.
Mm-hmm. Yeah, I mean, we look at all options, and it's all highly dependent on the environment and the cost. And increasingly, as we were saying earlier, with, for instance, satellite technologies, at the end of the day, it's always going to be a decision that is mainly primarily going to be driven by cost. As you would know from a, I suppose, rural deployment perspective, what really matters actually is the coverage, because again, that's what's going to make the deployment in a rural environment much more economically viable. Therefore, we are going to have to be looking at the lower end of the bands and the spectrum, and to an extent, it's even less relevant whether it's 4G or 5G. It's actually more about what type of spectrum band we can deploy in a particular area. And yes, as lower parts of the spectrum become available for 5G deployment, then we can look at those. But I would say that we're always going to look at a combination of, or the best combination of, if you like, radio technology, spectrum band, to achieve, I suppose, the most optimal or achievable, I suppose, cost base for a solution, and how that compares to fiber or satellite is going to be highly dependent on the environment. I'm not sure there is a single answer for that. But as to whether we're considering it, of course we are. It's just a question of, as I said, what is the cost analytics of each of the options available.
Okay. Right. And in about the 3 minutes or so we got, I've got one more question that kind of cuts across all three of you to some extent. Could be a bit contentious, but I'll ask it anyway. So there's lots of promises in the 5G space around low latency and ultra high reliability. And I know, there's been talks of sub 10 milliseconds and such with the low latency, and high reliability out to 6 or 7 nines in terms of the service functionality of it. So is this fact or fiction? And then does AI have a role in possibly enabling that? Okay, so Frank, I'll come to you first on that one.
It's fact. We are definitely targeting, those kind of parameters. It is going after particular mission critical, business critical type of systems. And one of the reasons why I have confidence that it's going to happen is Industry 4.0. So this is where the manufacturing players are screaming out for this. They're looking for high reliability, low latency connectivity in a wireless domain to enable their vision of how manufacturing is going to happen in the future, the highly flexible factory floors. So it's an instance where their research agenda, their strategic directions require what it is we're trying to deliver in 5G. It's not us trying to push the technology on them. It's them pulling it on us, from us. So it is going to happen, at least in that domain, and we will build from there.
Great. Maria?
I completely agree. And again, just building on that point, it's going to have to be about the impact that solutions like that are going to have on those industries, and you need to look at their business case. What is the cost of deploying a 5G solution to solve their increasing needs in areas like automation and so on, and what are the efficiencies and the cost savings that they are going to achieve out of that? And so long as those numbers look hugely positive, it's got to be a huge driver for us to address their needs. The additional thing I would say, of course, is that we don't need sub 1 millisecond everywhere, and we probably won't deploy everywhere because it doesn't make economic sense, and because not every use case or even service requires sub milliseconds. So I think we need to be very careful with, these ambitional, if you like, or target performance figures are in many cases only needed for a subset of the use cases, and therefore there will be a selective deployment of those capabilities rather than a nationwide rollout of sub 1 millisecond latencies, because you don't need that to check Facebook. So it's kind of different solutions to different parts of the market. The other thing to add on to that is the increasingly with 5G and some of the things that Frank mentioned, like network slicing and virtualization, that has come up a number of times during this afternoon's discussion. What we're aiming for is the flexibility to be able to do all of the above, is to have that selective rollout of the right features in the right places to serve different needs for different customers simultaneously, without obviously increasing the cost of the entire network deployment, which is probably where we have been up until now. So that additional flexibility is often missed, I suppose, in a lot of the talks or the discussions that we have, but it's absolutely key for this industry to achieve its objectives.
Great. Thank you, Maria. And Robert, I'm going to leave the last word to you on this one in terms of will or can AI enable this or accelerate it in some way?
So yeah, I'm going to use my academic experience, and okay, the simple answer, the quickest, is to set and extend a little bit, but we should not forget about fundamental limits. So the kind of promise that we're going to have ultra reliable, low latency communication everywhere that's just not true. They literally have fundamental limits. So I happen to teach coding theory. So that's the unit where we look at reliable communications over unreliable channels. And I always repeat students that there's no error correcting code in the world that corrects all erasures or all errors. So, there are limitations in the wireless channel, in the wireless world, that will then result in latency and reliability limitations. But beyond that, well, we in terms of point-to-point communications, we've done on the theoretical side as much as we could have done. At the protocol side, higher stacks, there's still stuff to be done.
Great. No, thank you. Thank you very much. So on that note, just looking at the time, I'm gonna bring this session to a close. First thing I'd like to do is to thank our presenters and panelists. So Maria, Frank, and Robert. But I'd like to thank everybody for participating and coming on board. Hopefully, we'll see you in more of the sessions later in the week. Thank you to the presenters. And on that note, I'll bring this to a close and hopefully see you in another session soon. So thank you.